Two-dimensional dynamics. We're continuing our study of dynamics, but this time bringing in another dimension. First, we're going to talk about resolving forces into two dimensions. Then what forces we have there. We'll work the inclined plane without friction. Then we'll add friction to it, and wrapping up with static equilibrium and the tension force. Resolving forces into two dimensions. So far in dynamics, only motion in one-dimension problems have been solved. All the forces were in the same dimension, typically either along the x or the y-axis. Yet there is a hint of two-dimensional motion in these problems. Where were forces in two dimensions used in solving a problem? Friction problems. If an object was moving along the x-axis with a friction force opposing its motion, the friction force was calculated by using the normal force in the y direction. So here's your y direction. By multiplying the normal force by the coefficient of friction, the friction force along the x-axis was calculated. There were two separate and independent calculations as shown here. On the y-axis, we had the normal force minus mg equals ma y. Now, if the object wasn't bouncing up and down, and we don't do problems where it bounces up and down, the acceleration is 0, so the normal force is just mg. The friction along the x-axis is negative because it opposes motion, so it's mu k times the normal, so it is mu k times mg, and that's a negative value. The various forces on an object don't always act in one direction. An example is when you're pulling a wagon. Here's our drawing of a wagon, and you're pulling it at an angle to the horizontal as shown here. Motion is this way, and here's our applied force. In order to solve problems using forces acting at an angle, like the wagon on a previous slide, the horizontal, x, and vertical, y, components of the forces must be found. The original force vector is now represented as the vector sum of its components. These components will show the motion of the object in the x and y direction independently, and when added as vectors will match the actual motion. Most of the time, it's easier to resolve a force into two perpendicular vectors on the x and y axis. Later on, there will be cases when the x and y axes will be rotated, but we won't worry about that now. That'll come when we do the inclined plane. Here's an Etch-a-Sketch drawing toy. This goes back many decades. The knobs, we'll look over here on the right side first, they move a metal pointer right here along this rod and this rod, scraping off a silver-colored coating to form a picture such as this. The combined motion can yield quite a complex figure, as shown here, but moving the X knob, that will move this here, only affects motion in the X direction, and the Y knob will only affect motion in the vertical or Y direction. But when you do both at the same time, you can get things like angle lines here, and then you squiggle them around. But each X and Y is independent of each other. So back to our wagon. It's being pulled down the street in this direction, and it has a handle that's not oriented either totally vertical or totally horizontal, but at an angle to the horizontal. That means the wagon is being pulled up and to the right at the same time. We start with a free body diagram. We have the normal force up, mg down, and we're going to assume friction here. So this is a force of friction, and here's our applied force. And we draw the acceleration vector over here. That's going to be very helpful very shortly. Now, a typical free body diagram would just have a dot for the wagon, but the wagon body is shown here to help you follow the forces. The normal force and mg both act in the y dimension and can be handled together. The friction force acts only in the x direction. So far, so good. But the applied force is a problem. It acts in both the x and y dimensions. We need to separate the applied force into its components along the x and y axis. What mathematical discipline will accomplish this separation? Trigonometry. First, we'll simplify the notation. We'll let F applied just equal F. The diagram here shows how f is expressed as the vector sum of fx and fy. Here's fx, so if we add that to fy, we get the total applied force. Another question, given that f and theta are known, what trigonometric functions can be used to find fx and fy? Oh, and by the way, these are all bolded to indicate that they're vectors. Right? Here's theta, that's just a scalar, but all our forces here will be vectors. We're going to use the sine and cosine functions to find the legs of the right triangle, just like two-dimensional projectile motion problems were solved in kinematics. So our force vector needs to be expressed in component form, with one component on the x-axis and one on the y-axis. Then they can be lined up in single dimensions with the other forces. Let's work an example when the pulling force is 50 newtons at 30 degrees with respect to the ground. Let's start with the horizontal component f sub x. We're going to use the cosine function, where cosine theta is adjacent over hypotenuse to find f sub x. So here's cosine theta adjacent over hypotenuse. fx is adjacent to the angle, right? It's right next to it. F is over here, that's the hypotenuse. So cosine theta is f sub x f. Move things around a bit, we get f sub x is f cosine theta. Plug in our numbers, and we get the force in the x direction is 43.3 newtons. Okay? That's less than the total applied force. So before we get to y, let's go ahead and add the horizontal or x component of the force, which is 43.3 newtons. We put it right over here, and we also draw the vector here, f sub x. And here's what the free body diagram looks like. Very much like the wagon, but without the red wagon. What are we going to do next? Vertical, or the y component of the original force. This time we're going to use the sine function, right? Because here's our angle. We want to find the opposite piece here. So sine theta is opposite over hypotenuse. Sine theta is f sub y over f. Move it around, and we have f sub y is f sine theta. Put the numbers in, and we get the force in the y direction is 25 newtons. So the vertical y component of the force is 25 newtons. We now add that to complete our free body diagram. Right over here. Here's our normal force, and here's f sub y. Sometimes people like writing the two vectors side by side, okay? Totally your choice. However, be careful when drawing the free body diagram. Ensure that the sum of f sub y and the normal force are exactly equal to mg. Why? Because the wagon is not bouncing up and down or getting pulled off the ground. Now, does it have to be exact when you draw the free body diagram? No, but just the closer you get it to this, the nicer it will be. So where are we now? Here's where we started. And one of the first things we did was we replaced f app with f, just to, write a few less things. And now we have these forces on our wagon. And notice you don't see f anymore. You do see f sub x and f sub y. And then when we just do the free body here with the little dot here as opposed to the wagon, that's what it looks like. We've replaced f applied with its x and y components.